So we'll talk about concavity today. We can use concavity to find points of inflection and also relative extrema. So let's think about why concavity would be helpful. So what if we know, like from the previous lesson, that at some point we have a positive slope, and so that would be good news if we're talking about profit in a business. But just because we have positive slope and we want to think about what's happening in the future, we would also want to know more about that slope, because if we could have a slope that looks like this, and that would be good. But if we had a slope that looked like this, we want to, and we see that even though it's positive, it's curving down, we would want to plan ahead for that. So that's curvature. We know that both lines, the blue line is increasing, the red line is increasing, but the red line has a negative curvature. It's also called negative concavity, and we use the second derivative to find that. Or we can, what if we have a zero slope, and we know the slope is zero, but with concavity we could tell if that's a max or a min. So in the first derivative test, we would check on either side to see if the graph is increasing and then decreasing, but with concavity we can just find out if it's curving down, and that would make a maximum, or is it curving up, and that would make a minimum. So we can use concavity to find relative extrema, and we can also use concavity to find a point of inflection. So a point of inflection looks like this, and it's where the concavity changes. So we have a graph that's curving down, and then it's curving up. So we have concavity, we have curvature, and the second derivative. So these are all the same, and in this example we have negative curvature, negative concavity, and the second derivative is negative. Over here we have positive concavity, curvature, and second derivative is positive. Okay, so for concavity and points of inflection, we need the second derivative. So the first derivative is negative 3x squared plus 6x. We need the second derivative, negative 6x plus 6. And let's find the possible points of inflection. Possible points of inflection are when the second derivative is 0 or the second derivative is undefined. So the second derivative is 0, and the second derivative is never undefined because it's a polynomial. And like we did with the first derivative test, let's check around the possible point of inflection And so we'll use a number larger and a number smaller. We want to find the sign of the second derivative at 0. So we put a 0 here. That would be 0 plus 6, and it's positive. Put a 2 here. Negative 12 plus 6 is negative. So when the second derivative is positive, the graph is curving up. And when the second derivative is negative, the graph is curving down. So we can see there's a point of inflection. And we can say f is concave up on negative infinity to 1. F is concave down on 1 to infinity. F has a point of inflection at x equals 1. And it did say find the point of inflection, so we'll say the point is 1, 0. No, it's not 1, 0. It's going to be, if you put a 1 there and a 1 there, it will be 1, 0. So at x equals 1, or the coordinates are 1, 0, because f double prime changes signs. So here we don't worry about whether it's positive to negative like we did before. It just needs a sign change. Let's do the same thing for this. Pause the video and try that one. Possible points of inflection are when the second derivative is 0 or the second derivative is undefined. The second derivative is 0 at 0 and is never undefined. And then we check on either side with negative 1 in the second derivative. That'll be a negative 20, and then put a 1 there and we get a positive 20. So the function is curving down with a, because there's a negative curvature, and then it's curving up because of the positive curvature. So we say h is concave down on negative infinity to 0, concave up on 0 to infinity, and it has a point of inflection when x equals 0, and the point would be 0, 2. If we put a 0 in there, we have a y value of 2. Because h double prime changes signs. Okay, so that's the procedure, and then the only way this gets more challenging is when we have a more challenging derivative to deal with. So let's just move on from there, because there's the procedure. Let's look at find the relative extrema. All right. Make sure that if you read second derivative test, you're not assuming that it's for a point of inflection. Point of inflection uses the second derivative, but the second derivative test is to find the relative extrema. So this one can be confusing because we have to find critical numbers. We don't just find we don't set the second derivative equal to 0. For the points of inflection, we needed possible points of inflection, so the second derivative is 0. But for this, we need critical numbers. Just like when we were doing the first derivative test, critical numbers are where the first derivative is 0 or the first derivative is undefined. So the first derivative is 0. And the derivative is first derivative is never undefined because it's a polynomial, so we have a critical number. But now we don't use a number line. All we want is the sign of the second derivative at the critical number, and here it's always positive. It's greater than 0. So let's think about what that looks like if we have negative 3/2. So we have a critical number, negative 3/2. Wherever the y value is there, we know that the curvature is positive, so it must be a minimum. And there's another mistake. You could say, well, this is positive, so it must be a maximum. You're connecting positive with maximum, but positive means it's curving up, so there's a minimum. So let's do f of x equals x cubed minus 9x squared plus 27x. Find the relative extrema using the second derivative test. Pause the video and try that one. So we need the first derivative, and we will use the second derivative later. We need to find the critical number. Critical number is when f prime is 0 or f prime is undefined. So now we have to solve this. Let's divide everything by 3. We can factor that, x minus 3 squared, square root, and we get x equals 3. Critical number is 3. And then we just test. We know that it's never undefined. So let's look at f double prime of 3. Six times 3 minus 18 is 0. So this tells us that there's no, or the test is inconclusive. We don't know what's happening with the well, if it's a max or a min, probably not. And if we wanted to continue checking, we would use the first derivative test. Okay, and we'll stop there.